The CTBTO Global Alarm System spans the entire globe. Its 337 monitoring facilities are located in 89 countries on all continents and cover all oceans. The system also features an international data center in Vienna and a global satellite communications network for data transmission. When an event occurs, several stations may detect and register the event. Data containing information such as location, time and magnitude of the event are recorded. Data are transmitted via the Global Satellite Communications Network, which is comprised of 5 satellites positioned around the globe at a height of approximately 36,000 kilometers. The satellites route the data to hubs on the ground. From there, data are transmitted through protected connections to Vienna. The entire data transmission from a monitoring station to the International Data Center in Vienna takes place in a matter of seconds. At headquarters in Vienna, scientists process and analyze the data in several steps. The raw data and the analysis results are then distributed electronically to member states all around the world. The white dots shown here are seismic stations. The seismic network is the biggest one of the CTBT Global Alarm System. It consists of 170 stations. 50 stations send data continuously. Another 120 send data on request. What you see here is the inside of the Earth. The red circles are seismic waves caused by an event deep in the ground, like an earthquake. Seismic waves cause vibrations in the ground. When they arrive at a station, they are detected by its seismometers. Here you see a typical seismic station built as an array. Some arrays can consist of up to 25 seismometers. This one has 10. They are arranged in 2 concentric circles with 2 seismometers in the center. A seismometer needs to be connected to solid rock to detect seismic waves most efficiently. At this station, seismometers are deployed at the bottom of boreholes. These boreholes can be up to 100 meters deep. With an array, one can determine from where seismic waves arrive. This helps to locate an event. Seismometers arranged as an array also amplify the seismic signal against seismic background noise. One of the 2 central seismometers covers a broader frequency range. It provides information on the depth and magnitude of an event. When seismic waves hit a seismometer, the instrument transforms the vibrations into electrical signals. These signals are then sent by radio to a central recording facility. There, computers record the data and prepare them for transmission via satellite link to the CTBTO in Vienna. The white dots you see here are radionuclide stations. 80 such stations are part of the CTBT Global Alarm System to detect nuclear explosions. Like this one. A nuclear explosion generates radioactive particles and gases. These radionuclides are dispersed by the winds. They may travel long distances from an explosion. Radionuclide stations are deployed to detect them. These stations are built in exposed areas as they rely on the wind. In an air sampler, radionuclide particles get trapped on a filter. Once a day, the filter is removed from the sampler and compressed. It is left untouched for 24 hours to allow non-relevant radionuclides to decay. The compressed filter is measured in a detector for another 24 hours. The result is information on the radioactive particles found on the filter. The detection of underground nuclear explosions is more challenging. Such explosions also generate radioactive particles and gases, but as you can see, the particles cannot escape from the underground. We have to rely on the radioactive noble gases as evidence. They seep through the underground into the atmosphere and are dispersed by the wind. Half of the radionuclide stations can detect such radioactive noble gases, in particular xenon. The detection process for noble gases is different. Air is collected as before, but only the gases are trapped. Xenon is then isolated and measured. The white dots that we see here are 60 infrasound stations. They monitor the globe for atmospheric or shallow underground nuclear explosions. Such explosions create infrasound waves, low-frequency waves inaudible to the human ear. This event here could be a volcanic eruption, a storm or an explosion, all creating infrasound waves that are registered by our infrasound stations. Such a station consists of several elements. This one has 8. The distance between the elements can vary from 1 to 3 kilometers. This is the best setup for trying to identify and locate the source of the infrasound waves. Each array element includes pipe structures to reduce the surrounding noise and amplify the signals. Filters at the end of these pipes prevent animals and dirt from entering them. When acoustic waves reach an infrasound station, the waves travel through these pipes to an infrasound sensor called a microbarometer. This is located in a vault at the center of each array element. It transforms the infrasound waves into electrical impulses. Each sensor transmits the signals to a central recording facility by radio or by fiber optics. This setup uses radio connections. At the facility, computers record the signals and prepare them for data transmission via satellite link to the CTBTO in Vienna. The white dots that we see here are hydroacoustic stations. Only 11 such stations are needed to monitor the oceans on Earth. This is because sound waves propagate very efficiently in the water. Here we can see an underwater event. This can be a volcano, an earthquake or an explosion. Sound waves are created and move through the oceans. And when they hit a hydroacoustic station, they are registered by its hydrophones. Hydrophones are sensitive underwater microphones. They convert changes in water pressure into electrical signals. They are deployed at a depth where sound waves propagate most efficiently. As you can see, hydrophones are arranged in triplets. This helps us establish where the sound waves come from. There are cables on the seabed to transmit the signals. Depending on ocean floor topography, these cables can be up to 100 kilometers long. Near the shore, the cable is encased in protective layers and then led through a pipe to avoid the rough surf zone. Computers at the shore facility record the signal and prepare it for satellite transmission. Dish antennas transmit the data via satellites to the CTBTO in Vienna.